Good evening, Chem Kids. I am going to go over how to do double and triple bonds. We're going to begin with carbon dioxide. And we see that carbon dioxide has one carbon with 4 valence electrons and 2 oxygens with 6 valence electrons for a total of 16 electrons. That is your total need. Carbon is going to be the central atom. We're going to put the 2 oxygens on either side, and then we're going to put 8 electrons around all the atoms because there are no exceptions. And this is a good time to review the exceptions. The exceptions are hydrogen wants 2 electrons, and boron and aluminum want 6. Everybody else wants 8. The problem is that if you count these electrons, you'll see that there are 20 electrons, which is too much, and it doesn't match this number 16. The number to always match is the number of electrons in panel 1, as that is the number of electrons that the molecule is bringing in. The way we fix that is that we think of, we're going to label these atoms A, B, and C. I'm going to insert 2 electrons between A and B, and because I inserted 2, I can now remove 4. I can remove 2 from A and 2 from B. That brings me down to having 18 electrons. That's still not the number that I want. I want 16 electrons. Now, I could choose to do it a third time and create a triple bond. I have a double bond now. But what I'm going to do for symmetry is I'm going to do the same thing but on the other side. Again, the technique is insert 2 and then remove 4. Since I inserted now between A and C, I'm going to remove electrons, 2 from A and 2 from C. I now have 16 electrons, and everybody still has 8. You're going to see a better depiction of this when I clean this slide up a little bit. This is now going to look like this. I'm going to count 2, 4, 6, 8, 10, 12, 14, 16 electrons. Everybody has 8 electrons. To get my shape, I'm going to look around the central atom, and carbon has a total of 2 areas of electron activity around it. Here's one area, here's the second, and of those 2 are shared, and none are unshared. So this is a 2, 2, 0, which is linear, and the bond angles on a linear are 180 degrees. Now here's another multiple bond. This is hydrogen cyanide, HCN, cyanic acid. And we're going to start by counting valence electrons. One hydrogen, 1 times 1 is 1. 1 carbon, 1 times 4 is 4. 1 nitrogen, 1 times 5 is 5. Notice how the least electronegative is in the middle since there's just 1 of every atom. 5 plus 4 plus 1 is 10 electrons. When I start to draw this, the only exception is hydrogen. I'm going to start with my central atom. I'm going to give carbon 8. I'm going to give nitrogen 8. And hydrogen is very happy with 2. Thank you very much. And everybody has what they need, except when you count 2, 4, 6, 8, 10, 12, 14, you have 14 electrons, which again is not a match for this 10. Once again, the key is to create multiple bonds. there's no way that I can put the double bond on the side between the carbon and the hydrogen, because that would give hydrogen more than 2 electrons. And hydrogen is one of those exceptions that we talked about that can only have 2 electrons. So I have to fix this on the side of the nitrogen by inserting 2. So this is what it looks like right now. I'm going to insert 2. And when I insert 2, I get to remove 4. Now remember, if you think of carbon as A and this nitrogen as B, I get to remove 2 electrons from carbon and 2 from nitrogen. That brings me down from 14 electrons down to 12. But I don't need 12, I need 10. So I have to do it again. I'm going to do it again on the other side. I'm going to insert 2. And I'm still inserting between A and B. And now I get to remove 4, 2 from A and 2 from B. And the only ones that you can't remove are the connecting electrons between the atoms. So you're not ever allowed to remove from the electrons that connect the 2 atoms together. Looks kind of messy, but the cleanup cleans up very well. This is a triple bond. We can see that there are 10 electrons, 2, 4, 6, 8, 10. We can see that everyone has what they need. The carbon has 8, the nitrogen has 8, the hydrogen has 2. And if you look around the central atom, which is the atom that helps you predict the shape, the Vesper shape of the molecule, we can see that this is a total area of electron activity around carbon of 2, and 2 are shared, 2 are unshared, or excuse me, 0 are unshared, and we're back to having a 2, 2, 0, which is another linear with bond angles of 180. One interesting thing is the diatomics. Remember the Hofbrinkels? HOFBr2, iodine, nitrogen, and chlorine. Okay, when you work these out, hydrogen has 2 times 1. So hydrogen's Lewis dot structure simply looks like this, which is HH. There's a single bond in between the hydrogen. When you do oxygen, however, you get 2 times 6, which is 12. And when you do the Lewis dot structure for oxygen, you're going to see that you're going to need a double bond for oxygen. So oxygen is one of those diatomic molecules that have a double bond. Fluorine is going to turn out to be single bonded because it needs 7 times 2, or 14 electrons. The same with bromine. The same with iodine. All the halogens, all 14 electrons. The same with chlorine. And it's not until you get to nitrogen, which has 2 times 5 or 10 electrons, that you see that nitrogen is going to turn out to be a triple bonded molecule. This is, I believe, in your PowerPoint as well. So of all the diatomics, everyone is single bonded except for oxygen and nitrogen. Oxygen is double bonded. And nitrogen is triple bonded, and all the others are single bonds.